All right, so the first thing is if you want to do exam 1 or 2 again, I put this exam redo questionnaire. It basically just asks you, I want to retake exam 1, I want to retake exam 2, or I don't want to retake either one. So if you don't really want to retake one, you don't have to answer it. Yep. No, I just use this to get an idea of how many test copies to make of each one. So you can actually say that I want to retake exam 1, but then you change your mind on Monday and you want to retake exam 2, and that's fine. Or you can change your mind on Monday before you look at the exam and not take any of them. What you can't do is start taking one and then change your mind. Once you start it, you're stuck with finishing it. So. But yeah, I'm just using this to get them, so I don't have to make 50 of each exam and only use 10 of one of them or something. So that's what it's for. Yep. Yeah, they're the same exact outline as the previous exam 1 and exam 2, just different problems, but the same outline. So wherever in the original exam 1 it said axial stress, then there'll be an axial stress question on the redo. It just won't be the exact same question. Unless I get really lazy and just like give you the whole test back, which I won't do that, but they won't be the exact same thing. So all this does is it goes in and it actually won't, I'm not eligible to take it. So you will be able to see some buttons where you can click what you want to do. And again, if you're not going to redo either one, you don't have to answer the question. It's not doing anything other than helping me kind of estimate how many of these tests print out, so I don't have a whole bunch of extra ones. I assume I'll have some extra ones, but I won't have a bunch of extra ones. I got 3 more trusses this morning in, so I sent them to the guy that's doing the cutting, so that's getting done. Let's see, what else do we have coming up? Quiz 5. One person has attempted quiz 5, so go ahead. I mean, it's not due until much later, but it is stuff that's on the exam, so I would do it before the final exam. And we're not covering any more torsion or power transmission, so work some of the web work problems, then do quiz 5, and should be good with that. If you didn't notice, the web work has all been shifted to where it's due on like the 14th or 15th. I don't remember the exact day, but even homework 1 and the challenging ones and the optional ones. Remember the challenging ones, CH 01, 02, and 03, those are bonus. So you actually get bonus credit for finishing any number of the challenging ones. The optional ones, the OP 1, 2, and 3, are just extra practice. So you do those. They're more like test questions, more like the level of test questions. So they're practice, but you don't get bonus points for finishing those. Let's see what else is in here. This is what we're doing today, is this thin-walled pressure vessel. Why don't we go ahead and get, it's a pretty straightforward topic. Let's get into it, and then whatever other questions we have, we'll talk about those. But this one is thin-walled pressure vessels. So we're talking about 2 different types. We're talking about spherical. Whoa, stay over here. And cylindrical. And so we're simplifying it a lot. There are cylindrical tanks that have spherical end caps on them and all that. We're ignoring what the ends look like. We're thinking of basketballs and Coke cans. So those are the shapes that we're kind of dealing with here. And thin-walled, meaning that the relative size of how thick the wall is small compared to the radius or diameter of the overall thing. So in particular, if we do the wall thickness, the ratio of wall thickness to radius, the vessel radius, we want this to be smaller than, so doesn't have to be equal to or less than 1/10. Sometimes you'll see this written as 1/20. That's when you're talking about wall thickness to diameter, obviously. So you multiply by 2. So in other words, the wall thickness is really thin. So like a Coke can, the wall of a Coke can is this super thin sheet of aluminum, and the radius of the Coke cans, I don't know, 1.5 inches or something like that. And so if we did the ratio of those, it would be much smaller than 1/10. Or if we did the diameter, it'd be much smaller than 1/20. Anyway, why don't we derive where these are coming from? So let's say we've got a sphere. Do a sphere first. So here's our sphere. And we want to cut this thing in half. So this is a sphere. And let's cut through the center of it such that we can see something like, let's see, I'll have to move it around. Something like that. Let's get rid of this part. But, whoops, it is a pressure vessel, so it's hollow on the inside. So I'm going to make it, you know, oh, but I'm drawing in white. That's not going to help. Let's say that it's like that. So there's the wall, and we've kind of sliced through the center of this. Now this one looks like it would not be classified as a thin wall because I made the wall pretty thick just because I want to draw on it. But that wall thickness, T, you know, that is the wall thickness. And inside this pressure vessel is a higher, normally it's higher pressure. I guess you could have some kind of vacuum thing that's not really what we're not really talking about these things imploding. We're talking about them possibly exploding. And so we have this pressure inside here. I'm going to draw kind of like it's a solid, but obviously it's some kind of liquid, air or water or whatever here inside here that's pressurized. And I've just sliced through it. And there's this pressure that I'll just lump into a single force P. So this force P is trying to explode the pressure vessel. And there's this stress in the wall, and I call that a force P. I actually want that to be a pressure, not a force. So there's this wall stress that's holding it all together. So the higher that P becomes, the internal pressure, the more stress is in the wall. We'll call this sigma A for it's kind of axial. Call it not a pressure, we'll call it stress in the wall. And so the higher this internal pressure gets, the higher the stress in the wall gets. If the stress in the wall exceeds the yield strength of whatever this pressure vessel is made from, then it deforms. And usually once it starts to deform, then it gets a bulge on it somewhere and it blows up because it's getting thinner and thinner at that spot, which causes the stress to increase because it's a smaller cross-sectional area and it blows up. So I can't do a pressure balance though, I can do force balances. So I want to change these into forces. So if I remember that a pressure or stress is equal to a force divided by an area, then I can rearrange that equation that say the force equals whatever the pressure or the stress is. So either sigma or P in my example, sigma A or P in my example. I'll just do pressure here, times area. All right. So the force associated with this internal pressure would be, so internal pressure. Would be the force there, we'll call it force from the pressure P, equals the pressure, which I've just labeled as a capital P, times the area that acts on, which if I look at this little green crosshatch area, that's the area, which is just the area of a circle. And it would be the area if I take the internal radius R. So R is internal radius. So that area is just pi R squared, where R is the internal radius. So I can do that. And then if I do the wall stress, similar thing, the force in the wall, I'll do that FW for the force in the wall, equals, I called it sigma A, is the stress in the wall. And that area would be, I could do it this way, right? I could say that area is pi R outer squared minus pi R squared, where R, regular R, is the internal. I could do that. And that would be, let's see if I can, this area. That would be this area. Which is right, but a lot of times when I have specific cases, like this is a specific case where it's a thin wall pressure vessel, I made it a thin wall pressure vessel for a reason. And one of those reasons is that it's a common thing. There are thin wall pressure vessels are common things, but also the distinction between thin and thick wall lets me do a little bit of not trickery, but I can change this up a little bit. So I can approximate this area with something else. So if I think about, let's draw this. So here's the area that I'm talking about. And again, it's a really thin wall, so it may even be thinner looking than that. If I were to take this area, which is the pi r naught squared or outer squared minus pi r squared, if I did that, but I split it apart right here and lay it down flat, then I get, oops, I don't get a circle. I get a, not green, but I get a big rectangle, right? So I kind of just cut it apart and laid it out flat, and I get a rectangle of the more or less same area. And as long as it's a thin wall, I get more or less the same area, where this distance is the circumference of the original circle, so pi times diameter, which I'm using r's instead of diameters, so pi times 2 times r. And again, I'm using the internal radius. And then times the wall thickness T. So I'm going to replace what I originally had that was the correct way to calculate this area of a circle inside another circle. And I'm going to replace it with the approximation of sigma A times pi times 2 times r times T. So this part is more or less equal to that part, as long as it's a thin wall. Obviously, when it gets thicker and thicker, then my splitting the circle apart and laying it out flat isn't going to give me quite the same area, because I'm using the internal radius, and I'd have to use some kind of midpoint radius type thing to get a better approximation. But these two now, this radius here and the one in here, are the same R now. I'm not using one that's the outer radius and one, I've changed everything to where it's just the inner radius. And I've got these two equations for force, one from the internal pressure and one from the wall stress. And I can do a force balance, because I don't want one of these forces. These are pressures on this picture, but they are from forces, and I don't want either of those forces to be out of balance, or else it really is going to explode, and I don't want that to happen. So I'm going to do, I drew this in more or less the x direction, so I'm going to do a summation of forces in the x direction equals 0. And I'll have, I drew the pressure, internal pressure in my positive x. So P times pi r squared minus the pressure or the force from the wall, which I said was sigma A times pi times 2 times r times t. That has, those two forces have to add to 0. So I've got the wall force and the pressure force, if those are names of things that you might want to call them. But I've got these two. So I can set these equal to each other, which I did. Well, I set them equal to 0, but I can rearrange the equation to say P times pi r squared equals sigma A times pi 2 r t. And I can cross out, there's a pi on both sides, so I can divide through by pi. There's a r and a r squared, so I can get rid of that. And now I've got an equation that says P times r equals sigma A times 2 times t. And I can solve this thing for sigma A. Sigma A is normally what I want to solve for because that's the stress in the wall that I can compare to the strength of whatever this pressure vessel is made of. So sigma A, the stress in the wall of the thin-walled spherical pressure vessel, equals P internal radius divided by 2 wall thickness. And I've got this nice, neat little equation that works for thin-walled pressure vessels. So some things you might ask are, well, way back up here, what happens if you cut it off and it's just a sliver of the sphere? You can do that, but that is a smaller wall stress, right? If you ran through the numbers, you would get a smaller equation for sigma A. So we've cut it right through one of the diameters of the sphere to get the largest possible stress in the wall. So this would be the worst case. And it doesn't matter if we cut it perfectly vertical or horizontal or at some angle, as long as it goes through a diameter, then that will generate the same equation. So it doesn't matter which way you rotate the sphere around. And it doesn't matter as far as maximum stress goes. If you chop off just a sliver of the sphere or whatever, this will be the maximum worst case scenario. Sometimes it might matter if maybe the way you made the pressure vessel put a weak point at some other location. I don't know how you would do that, but maybe you made a bad weld and it was a weak weld or something. I don't know why you would intentionally do that, but maybe you want to calculate the stress as if you cut it back here. This equation wouldn't generate that stress because that's a lower stress. So that's the maximum wall stress for let's write it in black. Max wall stress in a thin-walled spherical pressure vessel. All right. And so this would be the basketball. Basketball probably is pretty close, if not exactly, at a thin wall pressure vessel. It's got a relatively thick wall to its radius. So I don't know, I'd have to cut a basketball open and see how thick the wall is. But something in that kind of range where the wall is kind of thin, 1/10 the radius, and this equation would model that relatively well. Once you get into thick wall pressure vessels, maybe this is a much thicker wall compared to how big around it is, then this equation doesn't work because mainly we're assuming that, well, maybe this other picture, we're assuming that these stresses are evenly distributed in the wall, but if the wall is really thick, then it's going to have a variable stress from the inside to the outside of that wall, and these equations don't quite model that. Plus, we took this assumption or approximation for the area, which wouldn't work very well for a thick walled pressure vessel. in this course, I'm not going to ask you to, I'm not going to try to trick you by giving you a problem that's really a thick-walled pressure vessel and see if you recognize it. That's not the point of this. All the ones we do will actually be thin-walled pressure vessels. This might be a good question on exam 3, what determines a thin-walled pressure vessel, but I'm not going to give you one that's actually a thick-walled to solve. All right, so that's a sphere. So the other thing that pressure vessels look like sometimes are cylinders. So cylinder, obviously, let's see, how might we, if we look at it like this, I guess. Now, again, I said we're not concerned with what the ends look like. So a lot of times the ends are half spheres. And the end caps, the shapes of those do affect what goes on and how you model the stresses. They have different stresses in the end caps. We're ignoring the end caps. We're assuming that the end caps have no effect and they're not the weak part of our pressure vessels. So we're just looking in the wall, the cylindrical part of the pressure vessel. So it doesn't matter if it has flat ends or spherical ends or concave ends or whatever. We're ignoring all that. So one thing is I could cut this, somewhere through the middle here. And if I did that, its cross section would look a whole lot like the one we just did. In fact, it'd look exactly like it. We could go through the exact same derivation we just did for this, and it would come out the same here. So if I cut this part off, because it doesn't really matter what's going on over in this area. We're only talking about that internal pressure here and the wall stresses here. So, and that would look exactly the same. So the cylindrical pressure vessel does have, a lot of times this is called a longitudinal stress, assuming that this is like a longitudinal axis of the pressure vessel. And it looks exactly like this, PR over 2 times T. We go through the exact same process. So there is a longitudinal, and maybe sometimes they call this axial because it's along a longitudinal axis. So it might either look like sigma A axial or sigma L or longitudinal or something like that to signify that we're talking about stress along this longitudinal axial line of symmetry for the pressure vessel. And it is exactly the same equation that we just derived. But there's also another one. So we go back to our pressure vessel originally looking like this. This one that we just, didn't derive, but we said we could derive exactly the same way. That one talks kind of like it's exploding along the length of it. This part we drew is exploding away from the part that I erased. The same kind of thing could happen. Let me change from our curved ends into this one's just straight. And again, you do get these stress concentrations at the corners and all that we're ignoring. Actually, tomorrow we'll talk about stress concentrations, not really in the pressure vessel sense, but how we can take those into account. So what could happen here is I could split it this way. And, this part could come off of there. Now I need to maybe kind of modify this to make it look like a pressure vessel because it's round, or a cylindrical pressure vessel. Oh, wow, that's confusing me. Let's get it better. All right, so these little areas, right? Oh, that's too thick. Let's do it this way. Here Well, no, because I did the internal in green last time. This would be the green, the same green that we had before, where it's the internal pressure is on this area here. This area would be however long the pressure vessel is, so maybe L, and this distance would be, I'm going to keep things in terms of radius, so this is 2 radius, internal radiuses. So it's the diameter, internal diameter, but I want to keep the R in the equation. I don't want to have a diameter in the equation, so I'm going to say 2 times R. And then the stress in here is on these walls. And again over here. So there's actually 2 of these walls. Each of them have a thickness of T and a length of L. So this total area would be 2 of them, the front one and the back one, times the length, I called it L, times the wall thickness T. And then the pressure acts on an area that is L times 2 times R. So I can do the same thing where I have this internal pressure. Let's kind of draw it. Let's draw it red. So there's P, and I have this. This is not an axial stress anymore. I'm going to call this sigma H. So this is hoop stress. So the hoop stress only shows up in these cylindrical pressure vessels, doesn't show up in the spherical ones. All right, so if I get the force from the pressure, that would be pressure times the area the pressure acts on, which is L2R. And the force times the hoop force, I guess, we'll do H, is equal to the hoop stress times the area it acts on, which is 2 times length times wall thickness. And the 2 is the front area in my picture and the back area in my picture. And I do a summation of forces. I guess maybe that's the y direction. So in y equals 0. And I have the sigma h going up the way I drew it. So sigma h times 2 times L times T. And I did the pressure pushing downwards, so minus P times L to R. And I can set those, sigma H times 2 times L times T equals P L to R, and solve for the hoop stress. And I have 2's cancel out. Turns out the length didn't matter. It cancels out on both sides. And I end up with P R over T. Very similar, PR over 2T. So it is important to know the difference, because obviously this one, the hoop stress, does not have a 2 in the denominator, so it's twice the amount as the axial stress or the longitudinal stress. And so it is the one that is going to be larger when you have a cylindrical pressure vessel. So these are super simple equations to work with. The only tricky things are that the cylindrical pressure vessels do have the 2 different stresses, so you have to be sure which one you're solving for. If you're doing some kind of design or failure analysis, then you want the hoop stress. And technically that R is the internal radius. So a lot of times you might know the outer radius. It is a thin-walled pressure vessel, so the outer radius and the inner radius are really close to the same number, but technically they are different numbers. So this might show up some problem like, let's see. We have an example. We have a structural steel pressure vessel. We want, and it needs to be thin-walled, and we want it to hold an internal pressure P equals Well, let's think of it as a basketball. So that's like 18 psi or something. Except that we made a steel basketball, so whatever. And we have an outer diameter is, let's just make it 20 inches so it doesn't have the same number as, so it's something in the size range of a basketball, but a little bigger. All right. So what wall thickness for a factor of safety equal to 3 against yielding? All right. These are sigmas. They're axial. There's tension and compression. These are tension stresses, tensile stresses. So we need the tensile strength. We don't need a shear or anything like that. If we go to page 704, or some material property chart and look up our structural steel, we see that sigma y is 36 KSI. So we just get that out of a chart somewhere for this made up steel. But we want a factor safety of 3, so sigma allowable equals our yield strength divided by our factor of safety, so 12 KSI. All right. This is well, did I say it's spherical? I didn't actually say it's spherical. I said it was like a basketball, so that does mean that it's spherical. All right, spherical. So we only have to worry with the sigma equals PR over 2T. If it's cylindrical, then you need to do PR over T because that would be the higher stress. So our allowable stress is 12,000 PSI. Our internal pressure is 18 PSI. Our radius, internal radius, is technically, it is our outer diameter 10, or well, outer radius 10, minus the wall thickness to get the inner radius, divided by 2 and T. So we're trying to solve for T. So we have, to solve it, we have 12,000 PSI equals 18 times 10, 180. Those are PSI, or PI, I guess, I don't know, pounds per inch, minus 18T over 2 times T. So we have 24,000. I'm going to drop the units because they're actually confused. They're all in the right units right now, so they're confusing me. 24,000 T equals 180 minus 18T. So 24,000 minus the 18. So that's, see, putting the minus T in that numerator really doesn't make a whole lot of difference, but it does technically make some difference. Oh yeah, I do need to add it. Yeah, I don't want to subtract it. Still, doesn't make a big difference, but it does make a difference. Therefore, T is equal to 180 divided by 24,018. All right, 0.0075 inches. So all this does, though, is predict the necessary wall thickness for the pressure, the internal pressure to not explode. It doesn't count for like any other stresses that might be imparted on the basketball, like dropping it on the ground or something like that. But let's see. These kind of thicknesses are not totally, that's a super tiny thickness, but if we looked up the wall thickness of a Coke can, let's see, it's probably not a lot bigger than that. How thick is the metal in a soda pop can? No, not a useful answer. Oh, does it say it in here? Oh yeah. The thickness of a soda can is measured at more or less 90 microns. again, we'd have to convert that 90 micrometers to inches. 0035, so that's half what we just calculated, more or less. And so I think there's more coloring like paint on the can than there is metal, or in the same range as much. So some of these pressure vessels can be super thin like this, but it doesn't say that that's the only thing that you'd have to worry about. Obviously, if you have to do anything where these things have other stresses that you have to consider, then there would be other things. This only calculates being able to sustain the internal pressure. And if you think about like a butane tank or propane tank or something like that, they have a pretty thick wall because they get banged around and dropped around, and they have much higher pressures. They, 100 psi or something in there, 60 psi, I don't know, but more than 18 psi. So you do have realistic examples of this. Obviously, this would qualify. I guess you should check R or T over R equals 0.0075 inches over our inner radius would be 10 minus 0.0075, so 9.9925 inches. That's clearly smaller than 1 over 10. It is 0.000751, more or less. So way less than 1 over 10. So it would qualify as a thin wall pressure vessel. But these are the kind of, I can't ask something much more complicated than this for a pressure vessel. I could give you a cylindrical one, and then you have to know to use PR over T instead of PR over 2T. But they're pretty straightforward problems. You just got to remember the equation, which equations apply to which pressure vessels, shapes, and then that's about all we're going to do with them. We're going to take a very straightforward approach. A lot of times there is more to do with these because like a cylindrical one might be, it might have a weld line that goes spiraling around it to make it. And so you might want to calculate the stress on that weld line or something. But normally these are pretty straightforward problems to solve. You've got a couple of them in web work, I'm sure. Let's see if we can find web work. I don't know which homework set they are. They're near the end. There's one. So that's basically what we just did, except they gave you B. So this one is just calculating the stress. There's the same problem with the cylindrical one, so you got to calculate the hoop stress. That's the PR over T. There's another one where you're finding the pressure, and then it finds the wall thickness if you need a different pressure. So they're pretty straightforward. Shouldn't be any problem, but these are pretty much the type of problems. There'll be 1 or 2, probably 2 on exam 3. But they'll be on the simple and maybe the medium, but really the simple side of the problems that we'll solve. So they're pretty straightforward. Not a lot to say about pressure vessels. Yeah. I haven't made a list specifically. I don't think I have a list specifically already out there, but in general, it's about 1/3 of each thing. Let's see if I have an old list out here that I could look at. Here's a really old one. Yeah. This one, I'll have to update this particular list though, because, well, no, it even has that. This is more or less, I'll look through it and be sure, but this is actually really close to what it would have on there. So you're going to have stuff going all the way back to concurrent forces, so like a 2D equilibrium problem, and then stress concentrations, the stuff we'll talk about tomorrow. And then I don't know if I would make an angle. This one, so what this one doesn't have on it is deflection. I must have had that on exam 2 back then. So some of these problems are going to be replaced with beam deflection, because that is on our exam 3 this year, because we didn't put it on exam 2. So there'll be an easy beam deflection. That one I have highlighted will be a beam deflection, and I don't know if I have a third one or not, but there'll at least be those two, one in this range and one right here for beam deflection. Other than that, everything looks pretty correct. But no more problems. There'll be 16. There'll be 10 points on here. You got to draw a stress strain plot and label some points on it, and then answer some questions about some of these newer topics that we've talked about just recently. And then there'll probably only be 8 of these, 6 of these, and 2 of these. I'll make a updated list later today, hopefully, and put it up there. But it's very close to this one. What else? Oh yeah, so in your list of, you don't get the one, let me see. You don't get the one that I put in on the Moodle page. You get the one that's on Moodle, but in the general resources, right here. I don't remember what page it's on, but you get, let's see if this is it. Nope, must be in the other one. You get this chart right there with the 8 cases. I think the one that's linked as a web link in Moodle actually has 10 cases. You get this one that has 8 cases on it. And so you'll have that. And all of these little charts with the lines on them, those are the stress concentration charts. So you'll get those. Beam, and you'll get all the stuff that we've had from the first 2 exams also with the beam material and the centroids, the moments of inertia, all that kind of stuff. And you definitely don't have to derive or memorize the beam deflection equations. There'll be these 8 will be given to you. What else? Okay, then I think we're good. Tomorrow, if you want to follow along, we will be doing some SolidWorks stuff on the finite element analysis stuff. It's pretty we're basic. We're not getting very complicated with it, but it is interesting, and your SolidWorks will do this simulation, so you might as well see how to do it.